Victoria Roy. I'm the session chair for this session. Hope the tea break was good and have energized you. So to energize you more, we have three very, very interesting presentations from three very eminent researchers in the databases and data science community. So the first, we will have Professor Jayant Teresa. Jayant Teresa is on the Faculty of Computer Science and Automation Department at the Indian Institute of Science, Bangalore since 1993. He received a BTech degree from IIT Madras and the MS and PhD degrees from University of Wisconsin-Madison. He is a fellow of ACM and IEEE. He has given a very short bio, but as many of you know, he is a pioneer in the databases research from India. So please welcome Jayant Teresa.
So thank you for the generous introduction and good afternoon to all of you. What I'll be presenting today is work that we have been doing over the past couple of years in our lab on efficiently processing declarative queries. But before I get into the talk itself, I have a major confession to make. This is probably the only presentation in this entire conference which has absolutely nothing to do with AI or ML. So this is perhaps a good time to take a nap if you are a fan of those technologies. So today's world is civilized, modulo Trump of course, primarily because of relational database management systems. And that is because it is their heavy lifting which is fueling today's information age and digital economy. And on this slide, what you will see is the names of a few of the well-known database engines in both the commercial domain, like you have DB2 from IBM, you have SQL Server from Microsoft, Exadata from Oracle, and so on. And then in the public domain, you have both Postgres as well as MySQL, which are extremely popular. So database engines have been extensively investigated for over 4 decades now. And this is testified to by the plethora of top-tier journals and conferences that you have which feature research in this area, including the current COMAD. I didn't mention the word CORDS, I just said the word COMAD conference because the rest of the conference is going to be about CORDS. This one is the COMAD talk. Okay. So if you screw up the courage to go into the internals of a database engine, you will find that there are a small select set of core modules which provide its functionality. And these include, of course, the transaction processing module, which efficiently generates the ACID semantics for which databases are justifiably famous for. And then you have these various kinds of access methods that allow you to retrieve data quickly from the hard disk and get it into memory for processing. And then there is the actual memory management, which allows you to interface the database engine with the underlying operating system and the architecture. Now for all these three components, pretty much there's a general consensus in the industry at large as to how to go about building them. So for example, you would find that with regard to transaction processing, people generally used write-ahead logging, that's WAL, along with some version of Aries, which was developed by C. Mohan at IBM. And this is used for giving you transaction atomicity and durability. Similarly, some flavor or the other of two-phase locking is used for concurrency control. And then when you come to access methods, you use either B trees or hashing for domains with large cardinalities. Then you can use bitmaps instead for small cardinality domains. And then if you are venturing into areas like geographic information systems which have multidimensional objects, then you can use R trees. If you come to memory management again, you find that there is a version of LRU called LRU-K, and typically the value that is used in the systems is K equal to 2, which works exceptionally well for handling the typical database workloads. But then there is one more component, which is the query processing module of the database engine, which unfortunately, unlike the other three components, has largely remained a black art for the last 4 decades. Okay? And this is what I'll concentrate on for the remainder of this talk. So to motivate this problem, let's consider the simple relational schema for a university database where you have information about students, courses, and then the register table tells you which students are registered for which courses. And now, if you wanted to list the names of the students along with the titles of the courses that he or she is taking, then typically what you would do is to write this very simple SQL query, which is shown here, where you are basically combining the information between the student, course, and the register tables. Why are these join predicates that you see in the arrows here between student and register and between course and register here? And finally, you're going to project out the name of the student and the title of the course. Okay? So this is the schematic of what you will be using in order to interface with the database system to produce this particular answer. The key point to observe here is that unlike our typical programming languages, which are all imperative, SQL is a declarative or a procedural language in the sense that it only specifies to you as to what are the ends, but not the means to achieve them. Okay? So in this particular simple example that we saw, there are several things that have been left unspecified. For example, if you look at the order of doing the joins of these three tables, you could choose to first join S, which is student, with register, which is R, and then subsequently join it with the course relation. That's one option. Or for Vastu reasons, you may decide to instead say, let me join register with course first and then join it with the student table. Now, of course, you would know from your undergraduate courses in database management that the answers that you get from both these expressions would be exactly identical because the join operator is both commutative and associative. But the difference is that the amount of time that it takes to produce the answer between these two options could be enormously different. That is, it's possible that this expression would complete in a few seconds, whereas the other one, you may have to wait for your grandchildren to be born before the answer comes out from it. So when we say there's a big difference, we really mean that. Okay? It could be from seconds to years. That's the kind of gap that you have. Now, even if, let's say you went to an astrologer and were able to figure out what is the right join sequence to be used in your executing your query, what has been still left unspecified is how do you implement each of these logical join operators, which just says combine these two information. And if you are familiar with the database literature of the 80s and the 70s, you would know that producing new join algorithms was a cottage industry at that time. Okay? So there are a large set of options available here. You could, for example, use the classical nested loops join, or there is a sort merge join, or there's a hash join, there's an index join, there's semi join, and so on. So you would have to make a conscious choice of assigning each of these logical operators to a specific implementation of the join. Okay? Now, all this is going to be done automatically without your intervention, and this is done by the database query optimizer, which is a component of the query processing module. And what it does is it supposedly identifies the optimal evaluation strategy, which is typically called as the query evaluation plan, or plan for short. Okay? How do we define optimality? There could be many different metrics, but for the purpose of this talk, we'll assume that this is with regard to time. That is, you want the fastest execution of this particular query. So here is a sample execution plan. The plans are always a tree of operators that are evaluated in a bottom-up fashion. So in this particular case, what this is saying is that we will first join the course and the register tables. How do we do the join? By first using a B-tree index on the course table and a sequential scan on the register table, combine them after a sorting operation here using a sort merge join, and then do subsequently a hash join with the student table, and then out comes the answer. Okay? So this is one sample plan for executing the SQL query that we saw earlier. This is a physical implementation, that was a logical description. You would also notice that each of these operators that you have here is annotated with two numbers. One is a green number, the other is a red number. The red number tells you what is the amount of effort that is involved in executing this operator. So that is usually measured in terms of some notion of time. Whereas the green number tells you how many rows will come as the output of a particular operator. Okay? So just think of this as a network of water pipelines. Each of the operators is a valve. So the cost tells you how much effort is taken in opening the valve, and the amount of water that flows down the pipe is indicated by the cardinality. Okay? That's essentially what this is. So if you look at the numbers that you see here, as you go up the tree, the numbers become larger and larger with regard to the cost, because that is the aggregate cost of everything that you have to do done below you. And finally, when you come to the very top, this particular query, it looks like you require something of the order of 290,000 units of time to complete the processing. And then at each of the individual levels, you'll see that you have to estimate this cardinality, which is the number of rows that goes from one operator to the next downstream in this execution. So here it's, for example, 1,000, whereas in this case it is 10,000 and so on. Okay, so given this basic background, what database systems typically do is when you submit your SQL query, it goes into the database engine, and what the query optimizer does is that using a dynamic programming based strategy, it in principle looks through all possible plans to execute the query. The reason it's very important to look at all possible plans is there are a few very good plans and a large number of poor plans. So you need to actually sift through every one of them to find the right one. Okay? So it goes through this complicated exercise, and then out comes the optimal plan. And as I said, in our perspective for this talk, we'll assume that optimal means the fastest executing plan for this particular query. In order to be able to compare these different plans, because there's an exponential space of different strategies that are available, there are two models that are the input of the query optimizer. One model is the cost estimation model. That is the amount of effort that it takes to open the valve in the water network, as I said. This is the function of essentially the underlying hardware and the quality of the implementation of the database engine software. So this is essentially a given. Whereas the other model, which is the cardinality model, tells you how much data goes from one operator to the next in this flow of data through the processing pipeline. And this is a function primarily of the distribution of the data values, both within an individual column as well as across columns in the database. Okay, so all this looks fine and dandy, everything should be working beautifully. But what you'll find to your horror is that the supposedly optimal plan choice, which is at compile time thought to be the best way to execute this query or the fastest way to execute the query, may turn out at runtime to be actually highly suboptimal. And when we say highly, we actually mean highly. It's not by saying that it's slower by a factor of 20%, 30%, and so on. We would be given Bharat Ratnas for getting such numbers. When we say highly suboptimal, it is by orders of magnitude. 10 times slower, 100 times slower, 1,000 times slower, 10,000 times slower. That's the kind of numbers that we are talking about. Okay? When the query is executed with this plan. So the reason that you are having this discrepancy between compile time, what you thought was very good, and what is happening at runtime is that there are errors in the models, both in the cost model as well as in the cardinality model. The errors in the cost model don't affect you that much. There's a limited impact, usually of up to 30 to 40% or so they're not a major bottleneck. But with the cardinality model, all bets are off. This causes an enormous degradation of the performance of the system. Now, there is a large number of good technical reasons as to why this is a difficult problem to solve. But instead of going through, and these are listed here, but instead of going through all of these different issues in the interest of time, I thought I'll just give you a simple example to show you why it is so difficult to estimate cardinality as well in a database system. So here are two tables. One is the employee table, which has 1 billion employees. And you can see I have populated them with the names of the ministers of the local West Bengal state government. And then there is a manager table here. The manager table has 1 million managers, and these are populated with the names of the central ministers here. Okay? So given the love that is there between the central and the state governments here, I'm sure they would love to do a join between these two tables, which is, and let's say the join is on the age attribute. And if you look at it here, the age of all the employees is 25, and the age of all the managers happens to be 50. Okay? So now when I do a join of the age, so you're trying to find out which employees have the same age as some manager in this database. If you do this particular join, the output cardinality of the join will be 0, because none of the 25s will match with any of the 50s here. Okay? That's obvious. But now assume that one new employee joins the West Bengal state government, and that employee happens to be age 50. Okay? So this is the billionth plus 1th employee who is joining this table here, and that new employee has an age of 50. Now if you do the join, suddenly you'll find that the output cardinality of this join is that this new tuple will match with all of them here, and you'll get 1 million rows coming out of it. Okay? So earlier you were getting nothing, now you're getting a tsunami of data coming out from here. And the important point to realize here is that this was with a nanoscopic change. Okay, it's not in microscopic, it's nanoscopic, because there was 1 billion tuples here. You added 1 row to an enormous table, and all hell breaks loose here. Okay? So it is impossible for any summarization mechanism, including all the learning mechanisms, to capture such nanoscopic changes, because all of them are summarization models, and no summary can ever tell you that 1 tuple was added to 1 billion rows, and therefore 0 suddenly became 1 million here. Okay? So the whole system is extremely brittle. Now at this point you might say, well, this was an extremely contrived example, you made all the ages the same here and so on, this will never happen in practice. But unfortunately what is The reality in database systems is that worst case is average case. You will routinely get things to go horribly wrong. And if you don't trust me on this, here is a proof by authority. This is the picture of the handsome Guy Lohmann, who is the father of the IBM's DB2 query processing module. And in about 2014, he wrote a blog post in the ACM Sigmod site where he asked this rhetorical question, is query optimization a solved problem? And then he responded to this in fairly colorful language, where he says that the root of all evil, the Achilles heel of query optimization, is the estimation of these operator cardinalities. And then he goes on to say the cardinality model can easily introduce errors, not of 20%, 30%, and so on, of many orders of magnitude. And the last two lines are frightening. He says that with such errors, you should not be surprised if you get a bad plan. Instead, you should be really shocked and declare a national holiday if you ever get a good plan from a database system. Right? So, given all these errors, it's very unlikely that you will get good solutions for your queries. So at this point, you might say, okay, what the hell have this database community been doing for the last 40 years? This is clearly a bad situation, and haven't they been able to solve the problem even now? Okay? In fact, there has been extensive research done on specifically this problem for the last 4 decades, and you'll see some of these papers listed here, and you can see that there are numerous papers coming from the Sigmod, PODS, VLDB, ICD conferences, and so on. And they basically fall into 3 streams of or lines of attack. The first is to say that let me use more heavy-duty mathematics on this problem. So let me bring in things like wavelets, or let me use feedback via self-tuning, or today's favorite word for solving all problems, including world poverty, let's use learning. Or if I'm really good, let's use deep learning on it, and we'll get the solution. This is one approach to this. The other approach is to say that let me come up with plans that are in some sense amenable to errors, in the sense that they are robust to them, that even though there are going to be errors in the estimations of these various numbers that you saw going through the execution plan tree, in spite of that, the plan will work reasonably well. That is, the plan itself is robust to these errors. This is the second option. Or the third one is to do what is called as runtime reoptimization, where you start off assuming that the plan that you had was the right plan, but as you start executing the plan, you keep comparing between what you are getting and what you thought you would get. And if you find that they are similar, then it's perfectly fine, you made the right estimates, you keep going along. But if you find that there's a big discrepancy, then you go back to the drawing board and come up with a new plan. But now when you come up with a new plan, you know the exact values for some of the estimates that were earlier incorrect. So in that sense, you're going in with better information for your re-optimization in the second iteration. So if since this is a largely Indian audience, I trust that you would probably find this cricket analogy to be reasonable here, is that if you look at these techniques, this is like the VVS Lakshman style of batting, saying that let me be extremely sophisticated and stylish. Everybody remembers his late cut. Sometimes he would late cut the ball even after it hit the stumps, but still it was extremely elegant and so on. So this is one option. The other option is to have the wall in Rahul Dravid doing well, no matter what kind of pitch it is. He does a reasonably good job, and you can be sure that he's there to stay and give you a certain minimal set of runs. Or the third option is that we are all familiar with that Dhoni was supposed to be the master of adaptation, that you change from plan A to plan B to plan C dynamically as the game progresses. That's the third option which is here. But just like our Indian cricket team cannot guarantee you results, although Virat Kohli is trying to prove me wrong by doing well in Australia right now, okay, what you'll find is that all these ideas are very good. There's excellent concepts and formulations and theory behind them, but none of them can guarantee you performance. You will always have to go to the database system with your fingers crossed, with your toes crossed anything else that you can, go to Tirupati, break a few coconuts, and then come, then you may get a good solution for this thing. So what we did was to say that the problem itself is wrong, because nobody can estimate the cardinalities correctly except Rajnikant, and therefore we should change the problem itself. So we instead went in a different direction, where we say let's abandon this estimation process, which is being done at compile time. Instead, let's go in for a runtime discovery process, okay, which is what I'll talk about in the remainder of this presentation. And the nice thing about this new construction is that for the first time, you are able to give quantifiable guarantees on the performance of your system compared to a hypothetical oracle or God which knows all the answers in advance. Okay, so let's just look at how the current database systems behave on just a very simple one-dimensional space where you are trying to measure cardinalities. And instead of using cardinalities, I'll use an equivalent which is called selectivity, which is just the normalized version of the cardinality between 0 to 100%. So essentially what you can do is, let's look back at the query we had earlier, which is to combine this information of student, course, and register. And let's say there was this additional filter predicate called c.credits, that is the credits of the course should be less than some $1, where $1 is a parameter. So obviously if you give a small value for $1, like 1 or 0, then very few of the courses will qualify. If you give a large number for that parameter, then all the courses would qualify. So using the value of $1, you can change the selectivity or the cardinality of the course table, okay? Which you get a knob for doing that. That is what is shown on the x-axis of this particular graph that you have here, where you show the normalized cardinality, that is the selectivity, going from 0% to 100% on this axis. This is on a log scale. And that is done by changing the value of $1 along this particular axis. And on the y-axis, what you are showing is the cost of the optimal plan for executing this particular query. Because notice that with each different value of this parameter, that's a different SQL query. So this is a parameterized class, and there are several instances of it. So for each instance of the query, this line that you see here, which is the green line, tells you the cost paid by the optimal plan for executing the query. And again, notice that this is on a log scale, going from around 1,000 here to 1,000,000 here. This green plan is actually composed, this green line, sorry, is actually composed of many different plans. So for example, in this range of selectivity values, plan P1, which is shown with the structure which is here, where you first join course and register with the nested loops algorithm first, and then again do nested loops with the student table. Then plan P2 is a different orientation of this plan tree. Then there's plan P3, where you find that some of the operators have been now changed. So the physical implementation of the join now is a hash join and not a nested loops join, and so on. Okay? So you can go all the way up to plan P5 here. So there are different strategies that are ideal in different segments of the selectivity space, and this green line is composed of these 5 segments which is here. So if you took each of these 5 plans that you had, which each of them is a different strategy, and looked at their behavior over the entire space, this is how it looks. Okay? So for example, plan P1, which was very good at the origins of the space, is the red line that you see here, but at some stage it becomes worse than P2, which is the blue line, and then it takes off like this. Similarly, P2 is good up to this point, then P3 takes over, then P4 and P5 and so on. So the green line we saw earlier was essentially the infimum of this, all these 5 curves put together. So the difficulty here is that suppose you thought that the selectivity was going to be low, that it was going to be close to 0, but later because of this employee it jumped to 1,000,000, it's possible then that you're going to have a large number of values here instead. Okay? So you thought you're going to be here, but you turn out to be here. Or it can happen the other way around, that is you thought there are going to be a large number of rows, but it actually turns out to be very small. So what you can do is you can compute what we call the suboptimality profile, that is saying that how much worse can you get because of wrong estimates. So in this particular picture, for example, you will see at this location, you thought it's going to be a very small amount of data, but to your horror, it turned out to be a tsunami, as I said. So you thought it was going to be 1%, it turns out to be 99%, which means that you're going to use the plan P1, which is the plan which is here, at this location, which is where you are really supposed to have used P5. And if you look at the ratio of this performance, that's a factor of 20. Okay? Similarly, you can have the opposite extreme, where you thought it was going to be very large, it turns out to be very small. So you use the P5 in this region, and now you see that the ratio is 100. That means you are doing 100 times worse than the ideal in hindsight. So this is the worst case suboptimality is 100. Okay, so now let's look at how our system behaves differently on the same problem. What we will do is that we'll take that same green line that I showed you earlier, which was composed of these different plan colors, red, dark blue, brown, light blue, and so on. And what we'll do is that we will draw horizontal lines here. And there's a method to this madness. The horizontal lines are drawn essentially as a geometric progression. So in this particular case, you can draw it with a factor of 2, because this is on a log scale. They'll all be equidistant here. So you will see that the first line is at 12,000, then 24, then 48, 96, 128, and so on. Okay? This is what you will see. So in the second step, you'll find the plans at the intersection of these horizontal lines with this optimal curve that you had, which was the green line. And those plans which occur at the intersections, they form the plan bouquet. So in this case, it's P1, P2, P3, and P5. Notice that P4 is absent, because it's in between these two ranges. Okay, so now let's see what do we do with execution. Remember, our motto was never estimate. Okay? So we will not even try to do estimation. Instead, what we will do is, let's assume that the actual query was located here at 5%. We don't even know about it. We will first instead execute this P1 with this assigned budget, which is, let's say, 12,000. Okay? So you executed that. It won't complete. You just throw away the results. You start again. You execute P1 here now with this budget of 24,000. So you double the budget. It won't complete. Throw it away. Keep doing this. Eventually, you'll come to P2. You will now execute it with this budget, which is 192. Okay, 192,000 here. That also won't complete. Finally, you execute P3, which is what you see here, with a budget of 3.8 lakhs, and this is going to complete the answering the query. Okay? So this is what you're doing. It's a trial and error estimation process, but it's in a calibrated manner. So now if you look at the total cost incurred by us as compared to the ideal solution, which would have known that at Q sub A, which is 5% here, this is the right plan to have used, which was P3. This is the total we paid. So we paid 7.1 lakhs. The ideal was 3.4. So the ratio is 2.1 here. Okay? And you can slightly optimize this to get a 1.8 number. But at this point, you might say, well, you are just choosing a particular query that suited your thesis that you're going to be doing better than the contemporary optimizers. But if you plan this across, or profile this across the entire selectivity space for all possible locations of the actual query, you'll find that the blue line is what is given by our plan bouquet algorithm. So red is contemporary optimizers, green is God's ideal, and blue is where we are. And you see the worst case is not 100, but just 3. Now, the next question you might ask is, oh, this was for a particular query that you really loved, and this is what is showing this behavior. Maybe for my query, it's the other way around. Okay? So for that, we can actually show that there's a performance bound. So if you do that very trivial math that is here, you can show that the cost of the plan bouquet algorithm is essentially the sum of a geometric progression. If you compare this with the ideal, which is what God would have done because God knows the correct selectivities in advance or the correct cardinalities in advance, you can show that this suboptimality is bounded by this expression where R is the geometric ratio of the progression. And what you can also show is that this reaches its minimum at R equal to 2, which corresponds to the suboptimality being 4. So what this is saying is that no matter what, the performance of your query will always be within 4 times of the ideal. And you cannot also do better than that because you can also show that this is the best that can be done by any deterministic algorithm. So just to summarize what I hopefully gave you an introduction to, there's a lot more work on this, is that for the first time, the plan bouquet approach, because it throws away this idea of estimation and replaces it with discovery instead, is able to give you bounded performance suboptimality with provable guarantees. Okay? So if there are lots more details about the project which are available on the website. So all this started off with a concepts paper in SIGMOD 2014, and then there have been subsequent improvements. For example, I just showed you the one-dimensional version of the problem. The multi-dimensional are much harder to do, but we have had a sequence of students who have been able to make material improvements to the original solution. And recently, we have also been able to improve on the overheads that are involved in this initial process of creating the green line that I showed you. So these have appeared in these well-known fora. And if you're interested, you can please go and have a look at not only the project papers, but there's also a software demo there. And you can welcome to also download the software. And if you really like it, you're welcome to submit it also as your project in any of your courses. Okay. Okay. So with that, I'll end my presentation here. I'll just tell you that the takeaway here is that earlier, whenever we said that we had an SQL query and we said we would like to have optimal query execution, the dragon that used to come in between was, do you know the correct cardinalities or selectivities? Okay? And by doing this Gandhigiri approach of offering a few flowers to the dragon, you're now able to come up with near optimal query execution for this. Okay? So with this, I'll end my talk. Thank you for the patience.
Thank you, Jayant, for a very, very insightful talk. May I now request Lipika De, one of the co-chairs of this conference, to come and hand over a gift of appreciation to Jayant. Our next speaker is B. Ravindran. So to introduce him, Professor Ravindran is the head of the Robert Bosch Center for Data Science and Artificial Intelligence at IIT Madras and a professor in the Department of Computer Science and Engineering. He is also the co-director of the Reconfigurable and Intelligent Systems Engineering, RISE, group at IIT Madras. He received his PhD from the University of Massachusetts Amherst and his master's in the research degree from Indian Institute of Science, Bangalore. He has nearly 2 decades of research experience in machine learning and specifically reinforcement learning. He has held visiting positions at the Indian Institute of Science, Bangalore, India, and University of Technology, Sydney, Australia. He is also one of the founding executive committee members of the India chapter of ACM-SIG KDD, or IKDD, and is currently serving as the president of the chapter. His research interests are centered on learning from and through interactions and span the areas of complex network analysis and reinforcement learning. He will be talking about beyond rewards.
Lest you think when I'm talking about beyond rewards, I was moving away from realms of science and getting into spirituality. So this is my actual talk. And I know, Jayant, you are always a hard act to follow. And and so I did not, I'm not going to even try talking about things that we have done in the past. So this is actually work that is pretty much in progress. So I'm going to talk about stuff that we are working on currently. And also to accommodate several of the people in the audience who have heard me talk about reinforcement learning ad nauseum. Looks like I've been going around giving RL talks in many places. So I thought I'll talk about things I've never done before. Okay. Just a 2-slide introduction for the people who are just crawling out of under the rock, so who don't know what reinforcement learning is. It's all about trial and error learning, right? So the example I always give is think of how you learn to ride a cycle. Right? Nobody really teaches you how to ride a cycle. It's essentially you try things out, you fall, you get hurt, and you learn from the mistakes that you're making. Right? So the idea is that you're learning in some kind of a noisy environment, so you can't really write down rules, and so you need this kind of a error-based learning. And you end up making a sequence of decisions, and it's not that you don't get any feedback from the environment. And the way I would distinguish, the classical supervised learning from reinforcement learning is the following. In supervised learning, you get instructions about what is the right thing that you have to do. Right? So if I give you a position in a game, I also tell you, okay, if this is the kind of situation you see, this is the move that you have to make. And from several such instructions that you get, you kind of learn to induce a general rule on how to play games. Right? But in reinforcement learning, you don't get instructions. You first do something, and then you get evaluated. Right? You try to cycle, then you fall down, you get hurt, then that's the feedback that you get. So that is some kind of a feedback that you get, but it's largely an evaluative feedback, and as opposed to an instructive feedback. That's what really distinguishes reinforcement learning from the other kinds of learning. So there have been a lot of successful applications. I am not going to do hard sell on RL, right? And it's also behind a lot of the recent excitement in AI. So this slide actually originally read is behind most of the recent excitement in AI. And then I remembered that there's a very good chance that Rao and Ray would be in the audience today. So I changed it to lot and not most. Okay. And so the way you have to go about designing a reinforcement learning solution is that you have to decide on a few things, right? So one is what we call the state, right, of the system. So the state of the system is a description that has enough information, right, for you to take decisions. Right? It could be the positions of pieces on a board. It could be how fast you are moving, what's the angle that you're tilting in a cycle, and so on and so forth. Right? And often raw inputs are not enough, and you have to look for some kind of processed state. Right? And actions are the control variables. It could be the moves on the board, or it could be torques in the motor, and variety of things. So and you have to identify what are the actual actions that you need. Right? And so the rewards are designed in such a way that they communicate what the goal of the problem is to the agent. Okay? It is a very high level. Like I said, I'm not going to do this in great depth. And so we try to kind of encapsulate some of these in the form of a Markov decision process. right? So where you have the states, you have the actions, you have the rewards, that the feedback, the evaluative feedback that you are getting from the environment, and you also have a model, right, that tells you that if you perform an action in a certain state, what's the likelihood that you will move to a specific state, right? So that gives you the transition structure.
Okay.
Yeah, sometimes this collar mic works better. Even I can hear myself better now. Good. Great. So the goal of an agent is to learn what we call a policy, which is a mapping from states to actions, right? And you learn this policy in such a way that you get as much reward or as much evaluation as possible from the system, right? And so such a policy is called an optimal policy, right? And like a lot of work that's been happening in reinforcement learning. Reinforcement learning is at least goes back to the 80s, if not earlier, right? And there are several algorithms where people have talked about a variety of different things. And what is the recent more things like why everybody is doing reinforcement learning? So the way I measure it is the popularity of my reinforcement learning class in IIT Madras. So when I started teaching it back in 2004, I used to have like 5-6 students who registered for the electives. And right now, we had to shut down, like cards, we had to shut down registration at 85, right? And when we didn't, we actually have reached 100 students in the reinforcement learning course. And now we've come to a point where actually teaching reinforcement learning every semester. And with that, I have 85 students in my class. So you can imagine how things have gone crazy. And part of the reason for that is, the marriage of reinforcement learning with deep learning. And so in the earlier days, people, were complaining about how reinforcement learning has been limited to toy domains, right, where you have small grid worlds and things like that. Well, now reinforcement learning is limited to large toy domains like Visual Doom and Atari games and Defense of the Ancients and blah blah, so on and so forth. But still, there is a chance that we can actually do useful things with reinforcement learning, and more people can do useful things with reinforcement learning, not just a very, very careful handcrafted solution. So the talk, the theme of the work that my group has been doing over the past few years have been to explore learning more and more complex policies, not just as a simple mapping from states to actions, but to explore structure in the policies, and also to work with richer feedback from the environment, not just the simple rewards, but also to look at other sources of information that you can get from the environment, and see how you can marry the two in order to get more and more capable reinforcement learning agents. So, and we had to really thank DeepRL for this, because this allows us to look at complex domains where such structure can actually make a difference. I mean, I could have tried exploring this in small toy domains, but I wouldn't have been able to demonstrate the significant improvements in performance that we are able to do now, right? And so a lot of problems with deep reinforcement learning, and some of it, the people who have worked with deep learning know it's not unique to deep reinforcement learning. So as soon as you put any deep in front of anything, right, you're going to have some of these problems, like arbitrary choice of hyperparameters. So there's only so much that you can do, right? So finally, the machine learning people are feeling the pain of the database community, handling large volumes of data and trying to optimize things, performance at that scale, right? And so we have to worry about how we choose hyperparameters. And then, like I was saying, typically reinforcement learning systems learn kind of this flat mappings from states to actions. And if you think about how humans solve problems, right, we always think about a very complex structure. We think at multiple layers when we solve problems, right? So we don't look at, okay, here is the state, what is the angle that I have to bend my elbow at, right? We just think, okay, I'm going to reach out to pick a glass of water, drink, and then move on, right? So which I should have brought with me here. Now I realize that. Right? So there is no notion of decomposition with many of these deep RL things. So these are the pretty nascent areas that people are working on, right? And I could go on, right? But let's push on. So what are the things that we have been looking at? So we have been exploring structure and policies a lot, right? So we looked at learning, chunked actions as opposed to learning individual actions. So your policy is no longer just action for a state, but also how many times do you repeat the action in the state, right? So that's something. And then we have some work where we actually autonomously learn the decomposition of the problem. So we have some things that we have been working on for several years, and some recent work which I'm going to talk about today, right? And let's skip that. And we're also looking at learning with richer information, not just reinforcement learning signals, but can we look at, say, a human trying to solve the problem and get clues from that and solve the problem more effectively, not just driven by the reward. Thank you. And we also have a lot of explorations in robust RL. And in fact, I had to decide between giving the robust RL talk or the one that I'm doing today. So you're getting this one. If you want to know more about the stuff that we're doing in robust RL, talk to me later. Right. So in this talk, I'm going to talk about problem decomposition. Right. So I'll talk about this architecture called successor options that we are looking at right now. And I also talk about something we did with imitation learning, but trying to make imitation learning slightly safer. So this is what we call risk-averse imitation learning. Right. So this appeared in AMAS of last year now. Right. So successor options. This is joint work with a couple of my master's students, Rahul and Manan. So the idea here is that, so if I give you a problem, right, instead of trying to solve the problem from scratch, right, so I'm going to try and decompose the problem into potential sub-problems and then try to solve those sub-problems independently. So the example here is, are these one of those things where this works? Okay, great, yeah. So here I have a world with rooms and doorways between rooms, and instead of trying to solve the problem from scratch of going from one room to another, I basically decompose it into problems of go from exit a room through a doorway, right? So I'll have one decision that says, okay, go from here, wherever you are, go to the door. So that is another sub-problem that I'm solving. So I'll just solve these kinds of sets of sub-problems. So once I have, so in this case, I would have 8 different sub-problems because there are 2 doors per room. So I'll have 8 different sub-problems that I solve. And once I do that, now solving the problem of going from anywhere in the world to any other point, it's just essentially stringing together some of these sub-problems. I don't have to solve each sub-problem from scratch, right? And here is another example from a slightly more complex domain, which is that's a screenshot from a notoriously hard game for the reinforcement learning agents to play called Montezuma's Revenge, because it has a lot of things that the agent has to pay attention to, and the number of things it has to do before it gets an evaluation is very, very, very long, right? So it finds it very hard to learn efficiently in that kind of a domain, right? So you could potentially think of breaking it down into sub-problems like, okay, climb a ladder, get the key, this is a rope that you have to climb up and things like that. So there are different policies that you would need for solving each one of these different sub-problems. The idea is to, okay, instead of trying to just say solve Montezuma's Revenge, you learn bits and pieces, right? And then you put those solutions together. That allows you to learn faster. Right? This is the motivation behind why we want to learn this kinds of structured policies, like decomposition of policies, right? And so this is the sales pitch again. The idea here is to automatically learn this hierarchical decomposition, and we use something called the options framework, which essentially takes these sub-problems, right, finds a solution for these sub-problems, and treats those solutions, those policies that you have, as individual actions over which you can learn at a higher level. Right? So that's basically what the options framework does. There's a lot more mechanisms behind it, but that's a good enough representation for us. Right? And so typically, the option discovery methods that you have in the literature, they try to find what are called bottlenecks, like the doorways. So these are states or like kind of funneling states that based on your dynamics, where you have to go through specific points in state space for you to explain, for you to solve the problem. And so you basically find these kinds of bottlenecks in your state space, and then you use that for defining your options, right? So what we do is change it slightly, flip it around, and we look at what we call our landmark states, right? So this, in fact, the idea of using landmark states for decomposing problem goes way back, right? So so this is an idea that comes from psychology. So you don't talk about, when you give directions to people, you don't talk about bottlenecks, but you talk about easily recognizable things, right? So you say, oh, this is the most typical thing that you have to do. So as soon as you see a place that looks like this, you're probably at the right point, right? So you're basically going to give things that are prototypical examples. So instead of trying to solve sub-problems that take you to bottlenecks, we'll try to find sub-problems that take you to, prototypical states. And if you have enough of these prototypes in your state space available to you, then you are able to navigate your domain a lot more effectively than just only focusing on bottlenecks. So that's basically what we are trying to do here. And so there are a few things that we typically end up having to compare ourselves against. And the most successful of the recent works in discovering this kind of option structure is what's called Eigen Options, right? So the idea here is that you can look at your MDP and look at the transition structure given by the MDP. Right? If you remember, the transition structure tells you if you're in a state, you take an action, what's the likelihood you'll end up in another specific state. So you can just build this kind of a graph based on that and define a Laplacian on the graph, right? And then use that to define some kind of a set of basis vectors over your state space, right? And you find options, right, that take you to the peak points in this basis space. So you basically try to go to points in the state space where the activation of the Laplacian is maximized. Right? So the idea here is that since you are looking at the random walk, you're looking at the Laplacian of the graph of the MDP, right? So these peaks in points will actually lead you to bottlenecks, at least in theory. But in practice, when you actually run it, you don't see that behavior happening. But the theory says that this should happen. So that's the idea behind this, and they did show this on a few interesting domains, and so we kind of take off from there and look at how we can define this, right? So the crucial idea that we build this on is what's called successor representation. So the successor representation idea again is not old, as you can see from the citations. Right? So Peter Dayan proposed this back in '93. Not too many people paid attention to it. The idea here was to come up with a way of representing states. Right? You remember? Right? So states, I said you need to have enough information for a state so that you can solve the problem or you can make decisions on the state. So what Peter Dayan said is, so instead of having a state represented by the instantaneous information, okay, look at what is going to happen in the future starting from the state, right? From this state, if you start and I actually behave in a certain way, right? So what are the other states that I could potentially visit? So it essentially tells me what are the things that I can reach starting from a specific state. So successor representation is, okay, what succeeds the state? I'm going to use that in order to represent what my current location is in the state space, right? And so the advantage of this is that, right, so this is something that we skipped over, and I apologize for the people who don't know the mechanics of RL, but there is something called a value function that we estimate. Okay, the advantage of using successor representations is that when the rewards, so remember the rewards tell you what the goal is in a problem, right? When the reward function changes, essentially the goal changes, the world remains the same. Instead of going there, I want to now go there. Right? Instead of re-estimating the value function for a policy, right, I can just take the product of the new reward function with the successor representation, and that gives me my value for the new policy. It basically gives me the utility of executing this policy in the new sub goal, right, new goal. Right? And of course, people have extended this later and talked about how to do this with deep learning, and so you have deep successor reinforcement learning using successor features and so on and so forth. So I should point out that the deep successor reinforcement learning paper was on archive for at least a year and a half before it actually got in somewhere, right? And so here is an example of how the successor representation is going to look like. So I'm looking at the state that's marked yellow there, right? And the successor representation for the state that's marked in yellow, right, is going to look like that, right? So there's a very high value for the state itself, right? And you can see that the value kind of decays as you move farther from the state, right? And then there's a bottleneck here, and you have to come here. So essentially, at this point of time, your at least, or not time, at this point in space, your successor representation falls significantly, because the chances of you visiting a state on the other room by random, right, by chance, right, so by when you're using a uniformly random policy is very low. Therefore, this is how your successor representation looks like for the state marked in yellow. So of course, you are not going to use this as it is, because for every state now, your representation becomes as large as the state space. Right? So you are going to use some kind of a parameterized representation for this, and it becomes a little harder to interpret what that representation is, and therefore I'm not trying to depict it here at all. Okay? Yeah. So the idea here is that, so we start off with a uniform random policy, and then we build the successor representations. That is a very nice compact way of building this successor representations, and then we try to find prototypical states based on the successor representation. Essentially do clustering on the successor representation vectors that we get, and then take representatives for each cluster and use those as my those as the goals that I'm trying to solve in using my options. So once I have a good enough collection of these, right, then we go back and try to solve any problem on this domain, we get very good performance. And it turns out that it's sufficient for us to use random policies, uniformly random policies, to discover these goals, because that gives you an idea of the structure of the domain, right? And so here is an example. Okay. I'm looking at my screen again because I actually have a clock running, so I'm saving Shaurya the trouble of flashing a slide. Yeah. No, I'm looking at my clock, so I know. Yeah, that's fine. Anyway, so here is an example of what happens. So this is a more complex domain. I don't know. Okay, this one is at least more visible. So you can see the walls here. So there's a lot of rooms. It's like a maze domain. And when run successor options, you can find that you are actually discovering options that are like distributed across different rooms, and they are kind of in the center of the rooms, and so on and so forth. And this is what Eigen Option gives you, right? And so it finds some useful options that are near doorways in the original thing, but it also kind of gets a lot of degenerate solutions. Every yellow square and green square that you see there is actually a sub-goal that the Eigen Option discovers, and you can see that it just kind of core dumped somewhere there, right? So it just put all the sub-goals in one corner of the room, and there are a few sub-goals that it discovers elsewhere, right? And so for people to get any kind of useful solution power out of these Eigen Options, they have to talk about options of the order of 100, right? So before they can solve problems more effectively, and while we can talk about options in the order of tens, right? And for solving this thing, right? So I'll skip this, right, because it really need more things. And here is the power of this kind of SR options, right? So the picture in the middle gives you the visitation frequency. It essentially tells you how much of the state I'm exploring when I'm using options that are defined by doorways, right? I have a lot of doors here, right? So I have a set of options that takes me to the door, right? And when I do this kind of exploration using these options, you can see that I typically tend to visit doors, right? I'm not exploring the whole state space, right? And when I use only primitive actions and try to do the exploration, I'm actually visiting a lot of the state space, but it largely depends on where I start from, how much I visit. For example, there is a whole bunch here which I don't visit at all, and a lot of energy is spent in the bottom left corner where I start, right? And this one is when I actually use the SR options, right? But I restrict the number of times I can pick options, to 1 out of every 50 actions. So every time I pick an action, roughly, the next 50 actions I should pick should not be this kind of extended actions, but should be the whatever is the low-level actions from the MDP. And you can see that there's a lot more uniform exploration that happens, and it doesn't matter what option discovery scheme you have. This kind of what to say, this kind of a cooling off period between successive option picks, right, allows you to have much more robust exploration, as I'll show you later in the slide. Okay, I'll skip. And here's some experiments that we did with the DeepMind lab. Right? This is like a visual environment, so this is the kind of inputs that you're going to get, and you have to figure out how to navigate. So in this environment, so it's lab stands for labyrinth, not laboratory. So the DeepMind Labyrinth environment, so you just walk through this kind of maze-like environment. And so you can see that everyone can see the red line, right? That's a good one, yeah. That's SR options, but with this cooling off period. So we call this SR new, where new is the period over which you can't pick another sub-goal option, right? And you can see that whether it is SR new or whether it is Eigen Options with the new thing thrown in, right, the performance has a significant improvement once you add this cooling off period, but SR options does give you a lot more faster initial learning, right? And yeah, so there are a lot more work that needs to be done. And in fact, we're running it on more complex domains and collaborative domains and so on and so forth. And in interest of making sure Shaurya doesn't have to flash another slide to me again, I'm going to ask you guys to come and talk about this to me offline. Okay, and but I'll just mention that this is joint work with Anirban Santra, who's still a PhD student at IIT Kharagpur, and one of my master's students, Abhishek, and the parallel computing group at Intel. And we had some interesting results. So black, right? Yeah. So the takeaway is, of course, the takeaway is important, right? So when we actually have a specific objective function that handles risk, when you add it to imitation learning, and you're able to do much better in terms of mitigating worst case performance. So, and in fact, when we actually did the rail work, right, there was not too much work that had happened on the imitation learning space and Risk-Averse. So it was one of the first things that we did. And so this is what I was telling you about, the number of papers that say reinforcement learning, deep reinforcement learning somewhere, right? You can see that the growth is almost exponential now, right? But despite all of this, there are many fundamental questions our community hasn't answered, right? And still plugging away at it. And hopefully, so Sriram, are you going to give some answers to this? No, okay. So fine, so I'll stop here. Thank you.
Thank you, Ravi, for the enlightening talk on one of the most popular topics of recent times, perhaps. So may I request another general co-chair of COTS Comat 2019, Surajit Chaudhary, to come and hand over a memento to Ravi. It's a happy COTS Comat joint family. Okay, our next speaker is Sriram Natarajan. Sriram Natarajan is an associate professor at the Department of Computer Science at the University of Texas, Dallas. He was previously an associate professor and earlier an assistant professor at Indiana University Wake Forest School of Medicine, a postdoctoral research associate at University of Wisconsin-Madison, and had graduated with his PhD from Oregon State University. His research interests lie in the field of artificial intelligence, with emphasis on machine learning, statistical relational learning, and AI, reinforcement learning, graphical models, and biomedical applications. He has received numerous awards, such as Young Investigator Award from US Army Research Office, Amazon Faculty Research Award, so on and so forth. He is an editorial board member of Machine Learning Journal, Journal of Artificial Intelligence Research, and DAMI journals, and is the electronics publications editor of JAIR. He has been an organizer of several workshops and conferences. He was also the co-chair for the AAAI Student Abstract and Posters at AAAI 2014 and 2015, and chair of the AAAI Students Outreach at 2016 and 2017. So he will be talking about human-allied artificial intelligence. By the way, we could not have time for the question answers for the invited speakers, but I believe they will be all around for the high tea and tomorrow as well. So please do catch them. We have to leave the give the room to the organizers for the poster session between 5:30 and 6.
Okay. Thank you for the kind introduction. I hope you can hear me at the back. Sorry if I'm a little loopy. I just reached today morning, and Parag put my talk at 5 to test me to see if I can actually survive. So I'm going to talk about human-allied artificial intelligence. It's following the two talks, it's kind of taking it slightly differently, in the sense that I'm not going to talk about specific work that we are doing, but rather give the broad picture of the type of research that we do. So who we are, like Milind said in the morning today, most of this is due to the PhD students in the lab. So I've been fortunate to work with several PhD students, but I'm going to mainly talk about the research of the 3 PhD students that have graduated. Of course, a lot of collaborators as well. What we do, we call ourselves the Starling Lab, and it's basically statistical relational learning, and I'll explain what that is briefly. So the way we think about it is we work on problems inspired by this outer set of hexagons and develop solutions in the inner spaces. So, for instance, we look at learning from electronic health records or learning from clinical survey data, and I'll talk about them briefly, looking at adverse drug events, and then developing machine learning-based, AI-based techniques for addressing these problems. So we work in the space of graphical models, a little bit on reinforcement learning, but more recently on human-in-the-loop learning, which is what I'm going to talk a little bit about today. We have experience working on optimization as well, and as I said, classical machine learning problems. So that's what we typically do. So when I think of the research that we are doing, the question that I'm asking is, can we build systems that can seamlessly interact with, learn from, maybe contribute to, and collaborate with a human expert? So it's more like collaborative problem solving, not necessarily adversarial learning. So here, human is an ally. Can the machine and the human work together on solving problems together, right? So when I think of human-allied AI, in the restricted problem space that we have been working with, I can think of 3 specific instantiations, right? So the first one is what we call as assistantship learning. This goes back to my PhD days, where we are interested in developing assistants for the human. So think of an assistant that's sitting inside an electronic health record. A human walks in, the physician takes a bunch of information and then asks the human, okay, have you told me everything? And the human might say, yes, I've done. So the patient says, yes, doctor, I'm done. So then the physician could be recommending some treatment plans, and the system could pop up and say, hey, do you know that he has diabetes? And you're prescribing a particular tablet or a particular pill that could increase his sugar level. Maybe a steroid has been prescribed. So the point is that the assistant, which is residing inside your clinical decision support system, can actually help the human make better decisions by serving as an assistant, right? So you can think of it as a personal secretary who organizes the information in a better manner. A simpler instantiation of that is what is called as apprenticeship learning. We have a PhD student, Dr. Mike Skinner, who's actually a clinician. He's a pediatric surgeon who's been a surgeon for 35 years. He's a PhD student in my lab. And the problem that he brought in is classic apprenticeship learning. So the surgery that they perform on children, he writes these post-operative notes, right? And most of the times, it's the same thing that he dictates, or so he thinks, right? So what we did was we did a simple string similarity matching of all the documents that he had written. No 2 documents matched, right? So if you just do a simple string similarity, there was no match. On the other hand, if you look at semantic similarity, they're a lot similar, right? So the point he was trying to make was, can we somehow automate the simple task of writing post-operative notes? So offload a subset of the tasks that the human is doing to the machine, so the human can focus on other things, right? So that's apprenticeship learning. The recent project that our current PhD student Mayuk has been looking at is collaborative problem solving, and this is best summarized by Paul Cohen, who was the program manager then, and he said, think of the machine and the human as two children, right? So the machine tells the human, hey, you have a horsey, I have a horsey. let's take it to the park and figure out how to play. So both of these, both the human and the machine are being put into a new environment. We don't really know. It's like maybe the human is driving a Mars rover and figuring out how to navigate, how to search through this space, right? So I can think of several instances, but these are the types of problems that we are generally interested in, right? So, but of course, if you talk to people who are in industry, in the bank, for instance, there was a bank that tried to recruit me, and they said, oh, you know what? Here is what we need you for. And they said, we have a bunch of GPUs, but we don't really know how to optimize our deep network. And so we want to hire you, right? So that's what they think we do, is basically they give you a spreadsheet, and then you apply your favorite machine learning algorithm, AI algorithm. It used to be, back in the day, support vector machines in 2007, and then LDAs came across, go with the flow, apply it on the data. But that's not how life is. We just saw this beautiful talk about databases, for instance, right? So most of the data in the real world is stored in databases. If you start normalizing them and vectorizing them into a flat feature vector, you lose a lot of information. There's been a PhD thesis on this, where you lose, Jennifer Neville, for instance, has shown that you will lose autocorrelation and linkage information if you take a nice relational database and then convert it into a vectorized format to run your favorite machine learning algorithm, right? So, and look at this database, for instance. An electronic health record, it's messy, it's noisy, it's crazily interconnected. For instance, when I was working in Wake Forest School of Medicine, we looked at an electronic health record, and there were 4 entries for one patient, right? So the doctor prescribed medicine, the nurse had to give a different dosage of medicine because the patient had some reactions, and for some very weird reason, a different dosage was recorded. And finally, because we lived in the US, we still live in the US, the insurance is not going to pay for that medicine. So the pharmacy billed a different medicine. Okay? So for one person, we had 4 entries. How do you reconcile that, and how do you learn from this, right? And then, so if you think about the real data, it's mainly noisy, and they're all interconnected, right? So, and we have seen many talks, even in this conference, like the one on social networks today morning. So there's always this connection that between objects, between entities that happens, and that which we cannot ignore. But like Ravi was talking before, and I don't have to talk about this too much, is this repeated decision making under uncertainty, and in many cases with partial observations, right? So we have to repeatedly take actions, and the effect of actions may not come immediately, they're going to be long term. And somehow we have to reconcile with that and learn from this. So the point I'm trying to make is that we can't just think of data science as something where you take a simple Excel and apply your deep networks on it, and somehow magically sitting there tuning your hyperparameters for 5 days, suddenly you get great results, right? So if you really want to take and solve data science problems, we think it's a conglomeration of several fields that need to come together, right? So we need to scale them. Of course, mining and learning are there. Of course, computer vision has to be there. Search has to be there. We need to optimize several things. So data science, in my head, it's at least very interdisciplinary, and we need all these fields to come together. But what I'm going to focus today is a little bit on getting human in the loop with uncertainty and machine learning. So how can we get some form of uncertainty and machine learning? So what I'm really going to talk about are these 3 subsections in the next 20 minutes or so. First, I'll give you some background on what we do as our base learning method, and then talk about how can we bring the human in the loop in this base learning method. So our learning method is really based on gradient boosting. Many of you now know this as XGBoost. It's essentially a pretty simple idea. You start with some initial model that you have. You make predictions on this, compute the difference between data and prediction. They become your gradients. And then you fit a smaller model over these gradients. Instead of the original data, you fit the models on these gradients, and then make new predictions and keep going, right? So and till you converge. So the key idea is that if you think about it, the key idea is this is similar to AdaBoost, but here what you're trying to do is you go from your parametric representation. Let's say if you're interested in learning a conditional distribution, from a parametric representation like a conditional probability table, you move into a functional representation, which is essentially a non-parametric form. So you take your parametric representation, convert it to a non-parametric form, and suddenly what you can have is a set of weak classifiers which captures this non-parametric information. Okay, so this has been done again many times for different types of models, and for instance our lab has worked on learning cyclic graphical models, undirected models. Recently we have published and this is something that I'm kind of very proud about, because we've started publishing on continuous time models, and here for instance, one thing that you could show, which you couldn't show in the discrete time models, is that in continuous time models, this gradient boosting actually guarantees an optimal solution, because of the fact that you can show that the Hessian is concave, and hence the gradient boosting finds that optimal solution. Recently, we have started doing this on relational logistic regression, hidden data transfer learning, and so on. So there's a lot of work that you can boost using these conditional distributions. And the other thing that we have done recently is also doing this for multiple types of data. So we are not just doing discrete data, we can actually do Gaussians. Continuous time motivated us to work on exponentials. For Poisson models, we have to move away from this additive updates to multiplicative updates to guarantee some form of local optimum, but it can be done, and we are also getting some new results on Dirichlet distribution. So we can do different types of distributions, we can do different types of models, and we can pretty much apply them on many real data, and this is what I'm really proud about. All the way from a cardiovascular study to an electronic health record, to most recently we have worked with recommendation system, and I'll come to that in a little bit. So we've applied this across a variety of tasks, real tasks, and I've obtained results on these real tasks using this machinery, right? So the cool thing is all this code for all these models are publicly available. We have put them up in our webpage. Please take them, beat them up, and if you're using it for your class projects, something, we are more than happy to help you out. We'll provide constant support as well, and there's a really nice tutorial that my students have put together, and it's all publicly available. So use it, beat them up, and so on. So that's the foundational idea. Okay, the idea is very simple. We use gradient boosting. The trick is that we figure out how to do this on relational data, right? So using this machinery of statistical relational learning, which I did not go into because I wanted to keep this at a fairly high level, but the point is that you can learn relational models pretty effectively. With relational data, running these gradient boosting techniques can be pretty effective. So what I'm really going to talk about in the next 10 minutes or so is how can we bring the human in, right? So if you think about most AI research, they are primarily data driven. Nowadays it's deep, right? So it's just let's take some data set, throw a deep learning algorithm, and somehow hope that it works. Or sometimes it's fully expert driven. If the person sits down, writes a whole set of rules, and then you are learning from that. So on one side are the cases where you do pure supervised learning, where the human is restricted to be a mere labeler. He or she is there only to give you labels. And then on the other side is where he or she is a full knowing oracle, kind of tells you the complete model, right? Somewhere in between you can have these, let's say when learning a graphical model or something, you can have these weight learning or parameter learning, expectation maximization kind of things, which are closer to still somebody gives you the qualitative structure. The quantitative structure is what is being induced from the data, right? And then on closer to the example side is the classic active learning feature selection ways, where the system picks an example, but the human still only labels the examples, right? Somewhere in the middle is this notion of advice giving, right? And this is not by us. This has been done for like, 50, 60 years, right? Marvin Minsky's advice taking systems were a big deal in 60s, right? So all the way from Marvin Minsky to recently Jude Chawlik about 20 years back have been working on advice giving. So what is this advice that I keep talking about, right? So I work a lot with clinicians, and one of the things that you can get from them are what Benjamin Kuipers calls as qualitative constraints, qualitative reasoning, right? So you can get things like monotonicities. As the blood sugar level increases, the risk of heart attack increase. Simple qualitative structure, which talks about how when the feature value increases, the target value increases. Okay. Another good example would be something like a synergy constraint. You could say something like higher blood sugar level has a higher risk for high BMI patients than on low BMI patients. Now you're talking about how two features can influence a third one. And you can go on and on and on. So those are synergies, monotonicities, anti-synergies, and so on. So we can work with that. The other classic example is the precision recall trade-off. This is something that is extremely important, but that's been ignored most of the times, right? So if you think about clinical decision making, and I'm predicting, let's say, Ebola, then think about what is the effect of false positive versus false negative, right? Let's say the positive class is Ebola. If I say there is a false positive, okay? So what am I going to do? I'm going to quarantine a few more people, okay? They're going to sue me, maybe $1 million each. I quarantine 10 people, then it's going to be $10 million, right? On the other hand, if I release a couple of people who have Ebola into the general public without properly giving them treatment, I'm already creating an epidemic. Okay, there the false positive versus false negative, you kind of have to balance, and you can say maybe you should minimize the false negatives than false positives, right? On the other hand, LinkedIn today morning sent me an email saying, research associate, Precision Health, Indiana University. I am one of the freaking PIs of that grant, and I get an email saying, I have a postdoc position for me in my grant. Okay, why does LinkedIn do it? Because they only try to maximize most of the time everything that comes to you, right? So they are not interested in just maximizing precision, they are interested in maximizing recall, and that's a bad thing. You are not interested in everything that is relevant to you, you are interested in the most important things that are relevant to you. So a job recommendation engine exactly has the opposite issue. Okay, there you have to maximize precision, whereas in a clinical decision making you have to maximize recall, and you have to know the difference when you're designing these systems, and it's extremely important that we know this, and we have ways of providing this. The last one, actually the last but one, is on preferences. Then again, this goes back to Craig Botelier, where you can think of providing preferences over labels, and I'll give you an example. Okay, so for instance, a classic example would be I'm seeing these cars go by in a university town, in let's say in a college town in the US, and only 50% of the people stop at stop signs. What do you want to do, right? And then you could say, well, if it is safe to stop in a stop sign, you should stop. And that is kind of a preference knowledge that you can bias your learner to do better. And the last one, which Wapnick calls as privileged information, is kind of important. It's like giving hints during training, but that cannot happen during testing. So there could be extra features during training, for instance. So classic example is Alzheimer's prediction. Let's say I'm looking at a clinical study, fMRI data. There is this thing called ADNI, Alzheimer's Disease Neuro Initiative, and there I can get data all the way from electronic health records to imaging to actually cognitive tests. And recently they are also putting people in smart homes, and we can get these smart sensor data. So I have sensor data, I have cognitive test data, I have images and electronic health records. But at the time of diagnosis, when a patient walks into the clinic, I don't have the sensor data, I don't have their cognitive test, I only have the electronic health record and the image that is being put in front of me. And we have to make decisions based on this during deployment time. But at training time, I have these extra information. So the question is, how can I use this information to bias my learner so that I learn a better model, right? So the point I'm trying to make is what we have done is we have really applied this on a whole bunch of things. Again, I'm just teasing in this talk. If you really want more details, I'm happy to talk to you today or tomorrow. So we've done this in the context of probabilistic graphical models, and we recently have started working on causal models. I don't think you can read this example here. This is on, for instance, predicting postpartum depression from the social interaction. So by boosting, for instance, we got some very good, interesting causal links. So for instance, predicting postpartum depression in women, marital satisfaction is an important thing. And whether there is marital satisfaction is actually caused by the infant's temperament. I'm a father of a 3-year-old. I can tell you that's exactly true, right? I mean, however he behaves is how happy we are. So causal models, we are learning them, we are learning general probabilistic graphical models. We are working on relational probabilistic models, boosting and so on, using these types of advice methods. On the other side, on sequential decision making, we've also been working on reinforcement learning in relational domains, inverse reinforcement learning, which is the case where I don't have these rewards that Ravi talked about, but you have a bunch of demonstrations of what are good, let's say, good actions, good policies that a person has performed, and you want to learn the rewards corresponding to those policies. And of course, imitation learning that Ravi talked about. So for instance, the one result that I do want to highlight is this work by my student Philip Odom, where we took this advice on these microscopic images of fruit flies, where there is systematic noise, because these images are very, very hard to segment, because these are very tiny microscopic images. They are very tiny regions that humans have to decipher. So the humans know that these regions exist, but they don't really label it, right? But they can tell you. They can tell you qualitative information. So what we have done is we took that qualitative information into our boosting, and we achieved 99.1% accuracy on this real data set. This is joint work with Reed Porter at LANL in Los Alamos National Lab in AAAI 2015, I think. So I'm really going to close the loop in the next 6 or 7 minutes. These advice, if you think about these advice, and these are motivated from support vector machine literature, they really are constraints, okay, in your learning method. So how am I using advice? They are essentially constraints. So an advice, for instance, tells you everything inside this black region is a black or a positive example. Everything inside this blue region is a blue or negative example. So they become polygons in your feature space, and they are essentially these constraints which constrain the set of positive and negative examples. Now, if you think about doing a user study, and we did a user study, humans are amazing. Humans are amazing. You know in what? In stating the obvious. Okay? They won't give you the most informative data. They'll tell you the most obvious thing that you could have learned from the data. Okay? So if you think of these as polygons, not all polygons are equally important. Right? So think of a student, right? And most of us can. All of us have a mental model of everything in our head, and only when you ask a question, it's going to be useful. If I just keep talking, nothing is useful, right? So you got to ask me questions, and that's when we have an interaction and we can learn. So for instance, in this case, there are some regions that are useless. This black region is pretty much useless, right? But there are some regions that are very useful. Maybe this black and this blue are extremely useful. Maybe this blue is more useful to learn a better classifier, right? So which of these advice should the expert give? So we said, inspired by active learning literature, which said, I'm going to exponentially decrease the number of examples, right? So if passive learning required NP examples, active learning provably requires order of log NP examples, exponentially fewer examples. Similarly, advice-based learning also is exponentially fewer examples. What if we start procuring advice actively? So instead of asking the human to label examples, can we ask the humans to give us advice based on examples, right? So instead of learning, so typical active learning loop is, I'm going to learn a model, and then I'm going to generate a prediction, calculate some uncertainty, pick the most uncertain example, get the human to label them. We're going to do slightly differently, where we are, instead of learning the model, we're going to learn a relational model, a policy, whatever. We make predictions. Now, instead of choosing examples to label, we'll give you a set of examples to give me advice over. So maybe the human can say, so for instance, let's say you are predicting elections in the US from 2016. You could go back and say, ask questions like, what happens if the governor is Democratic and it is a West Coast region? Or in the Indian election, what happens if it is a southern state? What happens if it's Bengal, right? Or the northeastern states, where this typical waves, you don't see that much, right? So the question is, let the system figure out what question to ask, and then the human could give feedback based on it, right? So that's what we were going for. Again, we have done it in the context of probabilistic graphical models, reinforcement learning, inverse reinforcement learning. We have a bunch of papers on these topics. So the one small topic that I want to talk about briefly is this recent work that we have inspired by the success of active advice seeking. What we have come up with is this notion of active feature elicitation, again because of a real problem that we are working on. So we are interested in working with the state of Indiana sorry, on predicting gestational diabetes, right? But the bigger focus was many of the women who have gestational diabetes are going on to have diabetes later. And we wanted to figure out, can we identify them early? So one thing that we have was this data called new moms to be. The new moms to be data, we had a whole bunch of data set. We had their demographic information, we actually had their sensor information, their sequence information. They were all in smart homes, and we got some rich data about these women. Okay, so when we, and that's about, I think it's about 120 women here, right here. Okay, and then what we did was we wanted to recruit more women. So we put an ad out, and there were already about 2,000 women applying for this, to be in this study. We don't have money for all of them. We can't sequence all of them. We can't put all of them in smart homes. So the question was, which of these women are the most informative ones for us to learn a better model? Does it make sense? So we are interested in identifying the most important women that we can recruit. And this is, again, based on active learning, but not in the classical way, because we know the label. We want to get the features, right? We want to get their sequence information. We want to put them in smart homes, and we want to figure out who are the most valuable women in order to get this. So we have taken initial steps towards solving this problem. I'm not going into the details again, but this is a problem that we have been recently working on. Again, we have, as I said, we are heavily inspired by this notion of precision health, and we've been working on cardiovascular data set where this is a data set that started in 1985. It's a study that started in 1985 at the state of Alabama. The people who are recruited in this study were between 18 and 30 in 1985. So they are now between 48, actually now it's to 2020, so it's more like 53 and 65 in 2020, okay? And over the years, we have started increasing the amount of data that we have collected. Initially, it was restricted to their demographics, their family history, social activity, and some lab tests. Now the lab tests have increased. We have sequence information. For some of them, we even have sensor information, like putting them on smart homes, their Fitbit activities, and so on. And now the question is, can we go back and look at the data and predict which of these people from 1985 are going to have a heart attack in 2015 and 2020? Right? So that's that study that we are working on. We work a lot with the design group at Indiana University, so where we were looking at clinical study data, predicting rare diseases, postpartum depression, gestational diabetes, by looking at the social interaction of these people and asking questions. So kind of asking questions that could take some of these plants outside the clinic, right? Some of these prediction problems can be done outside the clinic, and that's what we are looking at. And more recently, we have been working on adverse drug events and so on. So I think with that, I'm ready to take questions, and this QR code would directly take you to our lab downloadable software, in case you're interested. Thank you.
Thank you, Sriram, for the wonderful talk. Okay, so Manish, if you could please hold on the question, because we're just having the questions after this. You can just catch him. We didn't have question for the previous speakers as well. Okay, so so now that Parag had put you on this test of giving at a 5 p.m. talk, so may I ask him to give you the memento? And for those of you who don't know, Parag is one of the program chair for this conference. Thank you. So we have a half an hour break now. At 6 o'clock, the high tea starts. Along with the poster session would also start in this room. Poster session for the research track, Young Researcher Symposium, and the demo track. So the presenters, the poster presenters should stay here and set up their posters. Rest of you are free for next half an hour, and then the high tea starts, and please join us for the poster session at 6 o'clock here. Thank you very much.